Okay, you might have heard of the character Sherlock Holmes. Was he a researcher? Well, I would argue yes, because even though he was fictional, he used to use science to actually collect his observations and make predictions and conclusions. So I would say yes, he's a researcher. Okay, so in this lesson, we're going to look at how to plan and conduct investigations. This is over a series of 3 lessons. This is part 1, and we're going to look at how to be a researcher. Okay, so what's in this lesson? Planning and conducting investigations, looking at the design design of an investigation and choosing an appropriate methodology. There's lots of different ways of doing science experiments. So we're going to look at some of these. So here we're up to the experimental design phase. So we've already thought about our topic. We've already come up with a hypothesis, an aim, and a research question. And now we're trying to design an experiment to answer our question and to determine the aim. So what we want to do is write down everything that we think about in our logbook. So this is a brainstorming phase. So we want to think about, for our BPA investigation, we might have read that BPA is a chemical that has health concerns. So we might think about water. Chemicals that can contaminate might lead us to jot things down about BPA. And there's been a lot of talk about BPA containing plastics and their health impacts. There's no right and wrong way of brainstorming. It's just capturing all your ideas, because your logbook will be assessed as part of your investigation. So it's important to keep a record of all of these. So write down ideas in your logbook and date the entries. Write down keywords, anything and everything that comes to mind. Don't exclude anything at the moment. And in order to try and come up with a methodology, you might want to think about past experiments that you've done. You might be able to adapt something or change a different sort of variable. So keep everything open at the moment. So there are a number of different methodologies that we can use. And we're going to cover these in this lesson and the next lesson. So they include case studies, classifying and identifying information, a controlled experiment, which is what a lot of people choose to do, a correlational study, field work where we might go out and collect samples, for example, at a pond, literature review, modelling, process, product or system development, or simulation. There's just some of the different methodologies that can be used. And a methodology is a system of methods that are used in an investigation. So when trying to choose a methodology, it's often useful to think about what you do and don't have access to and constraints. So by doing this, that you can eliminate certain methodologies. So you might have access to the chemistry laboratory. You might have a limited range of chemicals and equipment that you're allowed to use. You might be able to use your laptop and internet for a literature review. You might have, say, 5 lessons to conduct your study. But you might not be able to use the food tech lab for experiments. You might not be able to use concentrated sulfuric acid because that would be dangerous. You might not be able to afford, the school might not be able to afford anything that's too expensive. And when you're looking at literature, sometimes things are written for university level and might not be understood by a VCE student. And then there might be some extra things that you could have. So for our BPA investigation, we used an HPLC machine, and that might be having access to a university laboratory. So constraints are things that limit what you've got access to. Okay, let's think about case studies. A case study is an investigation of a particular event or a problem which involves a real or hypothetical situation and includes complexities which would be encountered in real-world problem solving. So they can take various forms. They could be historical, involving the analysis of causes and effects, as well as a discussion of what has been discovered from a situation. It could be a real situation or a role play of a hypothetical situation where credible recommendations are given. It could be problem solving where a new design approach, a methodology or method is required. And it's a real or hypothetical situation that's investigated in detail. So an example, we looked last lesson at the development of the model of the atom, and various scientists conducted experiments and further refined the model of the atom at the time. So Ernest Rutherford, who was a New Zealand chemist, he was one of the researchers who conducted research into the atom. At the time, the atomic model suggested that mass was distributed evenly throughout an atom. And Rutherford was firing alpha particles at a piece of gold foil or gold metal and surprisingly discovered that some of them, not many, but some of them bounced back. And this was important because most of the time firing the alpha particles at the gold atoms, most of the time the alpha particles would go straight through. But the fact that sometimes they were reflected meant that there was a concentrated mass inside the atom, which we now know is the nucleus. So without Rutherford doing these experiments, we wouldn't know partly what we know now. As a result, the current view holds that the nucleus contains the majority of an atom's mass, and for this work he was awarded a Nobel Prize, which is one of the highest ranking prizes you can have in chemistry. Okay, the next type of methodology is classification and identification, and that's using properties to arrange and identify chemical substances. So classification is the arrangement of phenomena, objects or events into manageable sets, and identification is a process of recognition of the phenomena as belonging to a particular set or perhaps being part of a new set. And here we have some atomic models. So carbon is the black atom. Hydrogen is white. Oxygen is red. And lots of organic compounds can be classified according to the types of atoms and their arrangement. So this is a particular class of organic compound. This is actually an aldehyde, whereas this one is an alcohol group or hydroxyl group. So organic chemicals can be classified into various families. So by doing this, it enables predictions of how designed molecules might behave under different physical and chemical conditions. And a typical example would be in drug design or pharmaceutical design. So a whole family of pharmaceuticals might behave in a similar way. Another example is flame tests, which hopefully you'll do in laboratory this year. And that's where various metals emit light of different colours when they're heated, when energy is supplied. And you can think about fireworks. You've got orange fireworks, blue, green, etc. And the type of metal that's in the firework is responsible for the green colour, the orange colour, or the blue colour that's emitted. So that can actually help us work out the type of metal. So if we have a white firework, it could mean that magnesium might be present. Green could be copper. Red could be strontium. Lilac, sort of purpley colour, could be potassium. So that's a way of classifying and identifying as well. Okay, the next category, which is a very common technique or methodology, are controlled experiments. And it involves the following components: writing an aim, a hypothesis, and identifying variables, which we've looked at in the previous lesson, safely conducting an experiment, which is really important, reporting results, analysing the results and evaluating the experiment, and writing a conclusion. So the main steps in the scientific method. So here we have an example of colorimetry. And in colorimetry, it's analysing the concentration of, or how much substance is present in a given volume based on the colour. The colorimetry equipment measures absorbance, which doesn't have units. And we can see that if we put standards, these are standard solutions, into the colorimeter, we can see that we can draw this dotted line between the data points, and then we could put an unknown sample in, as long as it falls between those data points. So it might be the absorbance is 2, and we can come back and say, okay, our sample contained X amount, or 2.5 in this case, molar of substance. So this is an example of a controlled experiment where we look at the relationship between the independent variable and the dependent variable, keeping everything else constant. So in our BPA experiment, we have a method. So using a similar technique to the colorimetry, we construct a calibration curve, and then the test samples that have been stored under different temperatures, we determine from our calibration curve, we determine the concentration of the BPA. Okay, the next type of methodology is a correlational study, and that's understanding the extent of a relationship between the independent and dependent variables. And an example might be where the relationship is studied. The change in the independent variable causes a measurable effect on the dependent variable. And this is an example of a scientific report that's been published so that other researchers can read the results of the investigation and learn from them. And they found that there was a negative correlation between behavioural and physiological performance under ocean acidification and warming. And that's the purpose of the article. A correlational study actually looks at what we call a Pearson's R value. And here we've got a positive correlation. Here we've got a negative correlation. And an R value close to 1 means it's strong. And an R value close to -1 also mean it's strong but inversely correlated. An R value close to 0 means there's no correlation. So here there is just no pattern, no statistical pattern. So we can see that with this R is 0.4, the general trend is as we increase along the x-axis, we increase along the y, and we could plot a path between. There's quite a lot of variation. That's an R value of 0.4. R value of -0.4, it's going in the opposite direction. Again, it's not that strong. There are data points either side, but much more correlated than R equals 0. Okay. Another question for you. Oliver considered several methodologies for his investigation into the vitamin C content of orange juice. Which of these methodologies is not part of the scientific method? Have a go at this question. Okay, a literature review is an acceptable methodology. So is a correlational study. Conducting a controlled experiment is a very common technique that I'm sure that you'll do lots of practice in the next 2 years in the chemistry laboratory. The opinion of a writer in the Herald Sun, that is subjective and is not part of the scientific method. So that's our correct answer. Okay, so to summarise, you need to think about the resources that you have when you choose a methodology. You need to apply the scientific method to whichever methodology you choose. You want to record everything in your logbook, and your logbook will be assessed when your report is evaluated as well. So for case studies, you need access to a library or laboratory. For classification and identification, you need access to laboratory and or published databases. A controlled experiment, you need access to laboratory equipment and chemicals. A correlational study, you need access to secondhand data for analysis. So next lesson, we'll look at part 2 of planning and conducting investigations. See you then. Bye. So you might have heard of the term citizen science. As the name suggests, it involves volunteer citizens that contribute to collecting data of projects that follow the scientific method. And examples include Earthwatch, the Australian Museum, CSIRO, and Parks Victoria, and there are many citizen science projects that you might want to be involved in. So in this lesson, we're going to look at part 2 of planning and conducting investigations. So we're going to continue going through different methodologies. This time we're going to look at field work, literature review, modelling, product, process or system development, and simulations. Just to remind you, we're back here at the experimental design phase of our scientific method and our research process. So we've already looked at case studies, classification and identification, controlled experiments and correlational studies. In this lesson, we're going to focus on these other methodologies. So field work, if you're fortunate enough to be able to go into the field or into the earth as a laboratory rather than stepping outside your science lab, you might be able to collect some data. So here we have someone collecting water samples and measuring temperature and pH. So this is an example of collecting data in the field. It involves students conducting their own investigation to solve a problem or to investigate an issue at a specific location. So it's measurements and observations taken outside of the school laboratory. Students might take notice of the site's context as well as its significance to an investigation, prediction and or hypothesis. Measurements and observations are collected in the field. Some are measured in the field, some are taken back to the school, and the data is often analysed back at the school in the science laboratory. Okay, a literature review. Now, you've probably already conducted literature reviews in the first few years of high school, but it becomes more and more important as we go through VCE and into university. And that's looking at credible sources. So regardless of what kind of research you're doing, you need to make sure you're getting information that is credible, which is accurate, has authority, and is trustworthy. So types of credible sources include textbooks, so your Edrolo textbook, for example, journals where scientists publish their findings for other scientists to read. Examples include Chemistry in Australia, the Australian Journal of Chemistry, the famous publication Science, another famous publication Nature, another one Chemistry World. They're just all the names of some journals. Websites by reliable, trustworthy organisations such as CSIRO, Royal Australian Chemical Institute, the Royal Society of Chemistry, which is a UK organisation, but very credible, the American Chemical Society, and databases such as ChemSpider. Why are they credible? Because they're all authored by experts. A literature review involves the collation and analysis of secondary data and sources related to other people's scientific findings and or viewpoints in order to answer a question. So a primary source is an original finding. So if you measure temperature in the lab and you record that temperature, that is primary data. A secondary source refers to original sources. For example, when you read your Edrolo textbook, the Edrolo textbook is summarising other people's primary data. So secondary sources are those that publish other people's work. A literature review provides background information and can explain observed events or preparation to generate primary data. And it's frequently included in the introduction section of a report or scientific poster. Sometimes it's the only method that's used because doing experiments could be dangerous or too expensive. So for this is an example here. It's a review article. It's reviewing a whole lot of other people's work into hydrometallurgical recycling of printed circuit boards. And it's called a literature review. So it means scientists, in this case from Colorado School of Mines, which is a reputable organisation, they reviewed a whole lot of published papers and printed and published their report. So in our BPA investigation, we might refer, or we should refer, to the literature. So BPA stands for bisphenol A. It's a monomer, a small building block used to produce a strong plastic polymer known as polycarbonate. And here we have the author, the in-text citation, so that the reader knows that this information was written by Vogel, and Vogel is listed in the reference list. So Vogel is the surname. 2009 was when Vogel wrote it. And then there's more information that enables the reader to get a copy of that and read it for themselves. Other parts of literature review in our BPA investigation. In water-containing products such as drink bottles, BPA is known to leach when hydrolyzed by heat, pH, or microwaves. And that was written by the author was Lee and others in 2008. And once again, Lee is cited in the reference list so that the reader can actually pick up that paper and actually look for themselves. When consumed in the body, that's the BPA, it can disrupt some important hormone-driven processes. And once again, an in-text citation that relates to the reference list so that the reader, if they want, they can go and say, I want to learn more about this. I'm going to obtain this paper and read more about it myself. And it's really important to acknowledge what other people have done. First of all, so you don't plagiarise, but also to give recognition for the work that others have done. And in science, we build on each other's work over time. Okay, another really important methodology that's used in chemistry is modelling, particularly because we can't see atoms and molecules. So we often make models of them so that we can actually imagine and visualise what we can't see. So when trying to investigate and understand abstract or intangible relationships, concepts and ideas, scientists sometimes use models. And it's a physical, a conceptual, or mathematical representation. So a physical example could be a model of a water molecule. And in this instance, the red atom is oxygen, white or grey here is hydrogen, and we see it's got this V shape, which is really important when we look at the properties of water and the intermolecular forces. So oxygen is an electronegative atom, and it pulls the pairs of shared electrons towards itself, which means this side of the molecule is slightly negative and these sides of the molecule are slightly positive, and that has a big impact on the properties of water. So that's a physical model. We could have a conceptual model like the concept of the carbon cycle, which takes place on Earth over long periods of time, where plants absorb carbon dioxide from the air and change it through photosynthesis into sugars, which are used to grow the plant, which then get broken down into organic carbon, and the cycle continues. Or we could have a mathematical model. So this is the gas equation, where P represents pressure, V represents volume, small n is the amount of substance in mole, R is a constant, and T is temperature. So another type of model. Okay, so modelling is really important. During the COVID-19 pandemic, scientists came up with a model to understand what the COVID-19 virus might look like. So that meant that then they could start developing vaccines to target the structure. And there were, if we have a look here, we've got time over the x-axis and daily new cases of COVID back in early 2021. And we can see that in August and September, we had a big spike in number of cases. So the waves of COVID pandemic were also modelled. And that meant that then the health authorities could actually say to people, now you need to wear masks, or we need these certain conditions to avoid making this peak even worse. Okay, another methodology is product, process, or system development, and it involves the design of an artifact, a process, or system to meet a need. This may involve technological applications in addition to scientific knowledge and procedures. So an example might be to develop an alcohol-free wine, so with 0% alcohol. And that could be developed by using a technique to remove alcohol from wine that has already been fermented, and to remove that alcohol while getting an acceptable taste. So that's an example of this type of methodology. Okay, another really common methodology these days is our access to some fabulous simulations. Simulations can be used to conduct experiments without expensive laboratory equipment, and also bearing in mind that they can be conducted safely. So it's the modelling and manipulation of variables in a real or hypothetical situation, often because the variables cannot be controlled, or maybe the system is too complex, it's too large or it's too small, it's too fast or it's too slow, it's not accessible for VCE Chemistry students, or it could be too dangerous. Many fantastic simulations are published by PHET, which is the University of Colorado in Boulder. And this is an example here of a gases simulation. And you can Google PHET, these are free. And what we can do here is we can change the temperature of the vessel. We can put more particles in, and then we can simulate what's actually going to happen to them. So fantastic set of resources. Okay, another question for you. Which of the following are methodologies that might be applicable to a scientific investigation? Have a go at this question. Okay, conducting a literature review is a valid technique. So is conducting a controlled experiment. Likewise, studying the correlation between an independent and dependent variable. So D, all of the above, is the correct answer. Okay, so there are a number of methodologies to choose, and you need to consider what you have access to and what you don't have access to when you're trying to choose one of these methodologies. So consider the resources that you have when selecting an appropriate methodology, and use the scientific method for whichever methodology you choose. Record all your learnings in your logbook, including dates, so that you keep a good record of your investigation. Field work requires access to equipment and a research location. Literature review, you need access to a library or internet search. Modelling, you need access to molecular models. You could make your own out of plasticine, or you could use computer access. Product, process, or system development, you need laboratory equipment and maybe a competitor's product to build on. And a simulation, you need access to a computer and the internet. Okay, I'll see you next lesson for part 3. Bye. Welcome back. So in this lesson, we're going to talk about working independently, so by yourself, but also collaborating with others. So your teacher will explain when you'll do each of these. So you might work with a partner to conduct an investigation, but you might each write the report individually and independently using the same data. And all of these skills, working by yourself and with others, are important for life outside of the classroom. So this lesson, we're going to look at part 3 of planning and conducting investigations. So we're going to continue looking at planning and conducting investigations. This time we're going to look at equipment and procedures, error and uncertainty, the type and amount of data, sampling, how to work independently and collaboratively, and how to make and record changes. So we're still at the experimental design phase of the scientific method. And what we're looking at are the corresponding materials and methods that you'll write about in a scientific report or a poster. Okay, so with equipment and procedures, the equipment is the list of the items that you'll need to carry out the investigation. And this is important so that other people can read your work and duplicate what you've done and hopefully get the same results. So the equipment is the list, the procedure is the method, and it's a step-by-step method to follow. And it needs to be specific enough that someone else can follow your lead. You might want to base your equipment and procedures on a technique that you've already used, for example, an acid-base titration. It's important to ensure that you're meeting the aim of the investigation or the purpose by choosing the right equipment and procedure to answer the aim. So, example of equipment that you might use. If you're doing a titration, you could use a burette, a pipette, and a volumetric flask. If you're doing a colorimetry experiment, you could use a colorimeter. If you're determining empirical formula, which is the simplest ratio of atoms in a compound, you might use a weighing balance, a crucible, and a lid, for example. So the equipment is the list of apparatus, materials, and chemicals required, and the procedure is the step-by-step method that the reader can follow. Now, you might keep the more detailed versions of these in your logbook, and you might just summarise the findings for a report or poster. Okay, error and uncertainty, really important things to consider in your investigation. We need to be aware of accuracy and precision and measurement uncertainty. And you need to be able to distinguish between random errors, systematic errors, and mistakes or personal errors. Ideally, in experiments, we're aiming for data that is both accurate and precise. By accurate, we mean values that are close to the true value. So that could be published data. Precise data is data that is very close to the mean value of the measurements. In other words, how close the data is to each other. And we can use these targets to try and demonstrate accuracy and precision. So here we have high accuracy because we've met the target in the centre of the bullseye, and the data is close together, so it's both accurate and precise. Here we have low accuracy, none of the data points actually hit the target, and none of the data points are together, so that's low accuracy and low precision. Here the data is collected together, so it's high precision, but it's off target, so it's low accuracy. And here the data is accurate, but not consistent. So accurate, some of the data meets the target, but it's low precision. And a way of thinking about this is that the word accurate has got the letters true in it, and precise has got the letters from close. So that's one way you can try and remember them. So experimental values are accurate if they're close to the true or theoretical value, which we don't always know. And data can be considered to be less or more accurate when compared to the true value if that's known. Whereas precision, we're talking about when several measurements are made. They're precise if they're close to each other, and it's a measure of how repeatable or reproducible the measurements are. Okay, so when we're taking measurements of continuous values, such as mass, time, etc., there's always a degree of uncertainty. In general, analog scales are read to an uncertainty of 1/2 of the smallest scale division, and digital scales are normally read to the last decimal point. When recording continuous data, record both the value and the level of uncertainty. So if we're using a top loading balance that has 2 decimal places, our typical uncertainty will be plus or minus to the last decimal place, so 0.01 gram. If we use a more precise bit of equipment, like an analytical balance that can measure to 4 decimal places, then our uncertainty would be lower because we measure to the last decimal place. If we're using a 50 ml burette, we can generally read that to plus or minus 0.05 ml, which is 1 drop of solution. And if we have a 250.0 milliliter volumetric flask, its accurate, or its uncertainty, I should say, is plus or minus 0.1 mil at 25 degrees Celsius. So the uncertainty is a range of possible values where the true measurement could be found. The next thing we need to think about are random errors and systematic errors. And error is the difference between the true and the measured values. So random errors are distributed around the true value. And the random error shown in this graph here are the green crosses. Sometimes they're higher than the true value, which is the blue, and sometimes they're lower. So higher, lower, and they occur at random. Some higher than the true value, some lower. They can be higher or lower, and they can be reduced by taking multiple measurements and taking an average. So in a titration, you might look for 3 concordant titers. That means within a range of plus or minus 0.05 of a mil, and then take the average of those in the calculations. Systematic errors, on the other hand, are biased in one direction. They're either always higher than the true value or always lower than the true value. And we can see the systematic errors are shown with the red triangles here. So if the true value are the blue dots, then the red triangles are all higher than that true value. They can be due to errors in the experimental method, but we can reduce them by calibrating the equipment and using proper technique. So if we're using a weighing balance, make sure that the weighing balance is reading the true mass that's shown on the scales. Using proper technique, so making sure if we do volumetric analysis that we read the bottom of the meniscus at eye level. But systematic errors can't be reduced by taking multiple measurements. So systematic error, they're all biased in one direction. Random error, distributed evenly and can be minimized by taking an average. We've all made mistakes before, and we call mistakes personal errors. Sometimes when we're collecting data, we can see some data that doesn't fit, and we identify that as outlier data. So sometimes you can recognize that you've made a mistake. Maybe you've spilt some solution or something when you're trying to do a technique, If you recognise that you've made a mistake, record the data but don't use it in your report. So you should repeat the mistake if you pick it up as you're doing it. You include it in the logbook, but you label it and exclude it from the honest reporting of the data and an analysis. So it could be, for example, spilling something or misreading a value. Okay, we also want to think about the type and the amount of data that we're collecting. Quantitative data is numerical data, so involves numbers. So that could be volume measurements, temperature measurements, the wavelength of light, or counting the number of protons in an atom. Qualitative data is descriptive, it's non-numerical, and it's quite important. It could be the description of how shiny something is, its luster, whether it's dull or shiny. Its description of state, is it a solid, a liquid, a gas? If bubbles are present or have just been formed, or a colour change from maybe starting off colourless and then going light brown. So qualitative data is important, but it's non-numerical. And it's often important when observing if a chemical reaction has taken place. So don't disregard your qualitative data. The amount of data, precision can be determined by the range of data obtained. Precise data has a small range. Imprecise data has a larger range. And usually 3 trials are undertaken in order to calculate an average. And repeated measurements reduce the effect of random error. Processed data or calculated data is often reported as a measurement result. So, for example, in a titration, the raw data might be the first titer was 15.05 mil, the next titer was 15.00, a third concordant, so within the point plus or minus 0.05, the third might be 15.10. So what we do is we take an average of the 3, and the average concordant data is what we call our measurement result, and that's used in our calculations. So we're aiming for high accuracy and high precision. And there's a saying, we only want to, if we're building something and we're cutting wood, we want to measure twice and cut once. So it's often best to take more measurements and make less mistakes with the cutting. Okay, so sampling. Ideally you want a sample that's representative of a larger quantity. And this is straightforward if the substance is homogeneous. In other words, that it's distributed evenly throughout the material. You also want a sufficient sample size that reduces uncertainty. So you might choose a 10-gram sample instead of a 0.1 gram sample because there'll be more measurement uncertainty with the smaller value. And an example is when we're doing titrations. Increasing a titer from approximately 5 mils to more than 10 mils will reduce uncertainty, because this is 1 significant figure and this is 2 significant figures. Okay, right at the start we talked about working independently and collaboratively. So sometimes you'll be able to work with a partner to design and conduct an investigation, but most likely you'll have to analyse the data yourself and prepare your report individually. All changes and all observations need to be recorded in your logbook. Before you do an experiment, it's often a good idea to construct a table to put data into so that you can keep your data that you're collecting in an organised and systematic way. So one way of doing this is to write down your independent variable, including units, and have those listed in the first column. And then if you're taking measurements of 2 dependent variables, sometimes it might just be 1, sometimes it could be 2, then list the dependent variable, including its units, in each column, and then you can add the data in as you conduct the experiment. Also make sure that you include the date. Okay, so to summarise, there's many things to consider when designing and conducting investigations and selecting an appropriate methodology. The best tool to use, whether you're working by yourself or with others, is to use your logbook. Use it to record your decisions as well as your results and observations, and record everything. It doesn't matter if you don't need it later, but you'll be in trouble if you don't record everything that's actually happening, and date each entry. And so far, we're at the experimental design phase. Next lesson, we'll look at safety and ethical guidelines. So I'll see you then.